Welcome to the course on real analysis. In real analysis, we are going to see is countable and uncountable sets. First, finite. Here, I am going to define 5 things. In all the things, this A is any set. Let me write J be the set of all positive integers. If this is in one-to-one correspondence with Jn, then I can call this A is finite. Next one is infinite. For any set A, we say A is infinite if A is not finite. The another one is countable. For any set A, we say A is one-to-one correspondence with J, the set of all positive integers. This is called as countable. Countable sets are sometimes called enumerable or denumerable. Next one is uncountable. For any set A, we say A is uncountable if A is neither finite nor countable, or A is not countable, it is uncountable. Next one is at most countable. For any set A, we say A is at most countable if A is finite or countable, or if A is either one-to-one correspondence with J or Jn. A is said to be at most countable. Here, finite and countable are quite different. Finite means A is one-to-one correspondence with Jn. That means it consists of only finite number of arrangements. If the set is not finite, it is infinite. Then what about countability? Even though this A is an infinite set, I am able to give arrangements in the set. If this is so, I call it as uncountable set. Then we can move to metric space. A set X, whose elements we shall call points, is said to be a metric space if with any 2 points P and Q of X, there is associated a real number D of P, Q, called the distance from P to Q, such that first condition D of P, Q greater than 0 if P not equal to Q. Then D of P, P equal to 0 if P equal to Q. The second condition is D of P, Q equal to D of Q, P. The third condition is D of P, Q is less than or equal to D of P, R plus D of R, Q for any R in X. Any function with these 3 properties is called a distance function or a metric. Next one is neighborhood. Let X be a metric space. All points and sets mentioned below are understood to be elements and subsets of X. A neighborhood of P is a set NR of P consisting of all Q such that D of P, Q less than R for some R greater than 0. The number R is called the radius of NR of P. The next one is limit point. Let X be a metric space. All points and sets mentioned below are understood to be elements and subsets of X. A point P is the limit point of the set E if every neighborhood of P contains the point Q not equal to P, such that Q is in E. Next one is isolated points. Let X be a metric space. All points and sets mentioned below are understood to be elements and subsets of X. If P is in E and P is not a limit point of E, then P is called an isolated point of E. Next one is closed. Let X be a metric space. All points and sets mentioned below are understood to be elements and the subsets of X. E is closed if every limit point of E is a point of E. Another one is interior. A point P is an interior point of E if there is a neighborhood N of P such that N is a subset of E. Next, we have to do the plural theorem. Every neighborhood is an open set. Consider a neighborhood E equal to NR of P and let Q be any point of E. Then there is a positive real number H such that D of P, Q equal to R minus H. For all points S such that D of Q, S less than H, we have then D of P, S less than or equal to D of P, Q plus D of Q, S less than R minus H plus H equal to R. So that S is in E. Thus Q is an interior point of E. Next we have to move numerical sequences. A sequence is said to be convergent if it approaches some limit. Now we wind up the session. Thank you.